All right, good morning, everyone, and good afternoon. Hey, good morning, everyone. Thanks for being here. This is the 9th Canadian Underground Infrastructure Innovation Center Academy Webinar this year. And we have an honor, a great presenter here, talking about Reliably maintaining Arizona's largest aqueduct system, a review of reliability engineering at the Central Arizona project. Presented by Jim Geisbush, Senior Civil Reliability Engineer at the Central Arizona project. These webinars are organized by the Canadian Underground Infrastructure Innovation Center, or CUIIC, the University of Alberta, and Benjamin Media. CUIIC Academy offers classes, courses, webinars, and events to further underground infrastructure education opportunities across Canada. CUIIC Academy webinars cover a variety of pressing topics related to the underground infrastructure sector, and speakers include leading industry professionals who will provide a monthly free educational webinar to the public, followed by a brief question and answer period. Please join us next month on October 19th at 1 p.m. Eastern for Shifting Calls to Clicks, presented by Mike Sullivan, President of the Utility Safety Partners. In addition to the series, we will be holding the CUIIC Safety Academy in Edmonton on November 29th and 30th. That'll be the first time we're offering that. And coming in March 2024 in Richmond, BC, we'll be holding the second CUIIC Academy in Pipeline Rehabilitation. And both of these academies are two-day events with a variety of speakers and very timely kind of discussions related to the safety of rehabilitation of pipes. So they're very good, well-attended events. I want to thank our sponsor this year for the 2023 CUIIC Academy Webinar Series, MPIPE. Thank you very much. If anyone's interested in sponsoring the opportunities with CUIIC, please contact Hannah at Benjamin Media for more information about becoming a sponsor. All right, next, let's introduce our speaker. Mr. Geisbush has over 30 years of utility operations and engineering consulting experience working with water and wastewater systems, including raw water and irrigation. Jim has a bachelor's and a master's degree in civil engineering and is currently pursuing his PhD in civil engineering at Arizona State University with emphasis in construction engineering for large diameter water pipeline maintenance. He is a registered professional civil engineer in Arizona and California and a certified project manager professional. Jim is a senior civil reliability engineer with Central Arizona Project, CAP, where he's worked for over 7 years. His primary condition is CAP's pipelines and tunnels. So welcome, Jim, and I'm looking forward to your presentation. And there you go.
Thank you, Jason. I appreciate that. Good morning or good afternoon, everybody, depending on what time zone you're in. Appreciate the opportunity to come speak with you. When Dr. Lueke first asked me about giving this presentation, he said he asked me to make sure I showed some big facilities. So this first slide we have right here is the largest pre-stressed concrete pipe in the world. Because I actually need to correct that. It's one of 3. The other 2, we operate those as well and have those slightly downstream. As a reliability engineer, one of my tasks was analyzing the pre-stressing wires in this pipe, coming up with repair strategy, and this is the resulting maintenance activities we're doing one evening working on the pipelines. What I'd like to do is just give a quick overview of the Central Arizona Project, or the CAP, a lot easier to say that. Talk about the pipelines in particular, that's my primary focus of responsibility, and then talk about what does a reliability engineer do. The slide here on the right is the Colorado River. Actually, we're looking at Lake Havasu, which is the Colorado River backed up by a dam. Our first pumping plant is right down here. You cannot see it below the ground, but this is the forebay coming into that plant. And I take a moment to take a picture of this in your head, because I'm going to come back to it in a moment. We've got California right over here, and then this is all Arizona. Okay, so I give a lot of talks on the Central Arizona Project. And I half joke when I say we're just a water delivery company. We take water from point A and give it to point B. Point B being about 550 kilometers away, almost 1,000 meters higher in elevation. So we pull water from the Colorado River here on the California border and through a series of pumping stations, open channel canals, and pipelines. And what we're seeing in green are various pipelines we have along the system that typically go under bodies of water. We move the water to the Phoenix metropolitan area and then continue down south to the Tucson metropolitan area. And in between, we deliver majority of the water, about a third of the water source, to Indian reservations and irrigation districts along the way. We are a desert, and one of the things I want to point out is we get less than 20 centimeters of rainfall annually. In the last couple of years with the drought, we've been getting less than that. It takes a lot of infrastructure for us to move water across the state. So some of the major assets that we have are, we've got 15 pumping plants scattered along that 550 kilometers, 39 check structures, and we have multiple check structures between pumping plants to control the flow of water and to keep the elevations different in the pools as we need to make it for making deliveries to our customers. We turn out water to our customers through 49 turnouts scattered across the system. We've got 6 groundwater recharge facilities that we have been using to recharge groundwater off with aquifers, but with the reduction we've had to take on the Colorado River this year and last year, we are no longer doing any recharge. About 3 inline reservoirs that also help us regulate the flows through the canal, and one large offline reservoir with an earthen dam, and that's this picture right here, Lake Pleasant, an enormous lake about 20 minutes or so north of Phoenix, with a large earthen dam. What we're seeing here are the intake towers to the pumping plant. Actually, this is the pump generating plant. In the fall and winter, we fill the lake, pulling water off the Colorado River, and then in the hot summer months when electricity is very expensive, we're actually pulling water out of the lake and sending it down to our agricultural customers. One of the things that I do is roughly every other year, I get in the tunnels and the pipelines that go between the pumping plant and the intake towers, monitoring those, inspecting them, making observations, and then putting together whatever repair plans we need to do. On a typical year, we deliver over 1.5 million acre feet of water. That's 1.8 billion cubic meters of water a year. This year, with the reduction, we're only delivering about 1.1 billion cubic meters. But we provide water to about 80% of the state of Arizona. Over 5 million people rely on water from us. And to help us move that water, we've got about 480 kilometers of canal, about 16 kilometers of tunnels, and then about 65 kilometers of pipelines. So remember that first picture we looked at, our first pumping plant? I was standing up here at the outlet of the 2 steel discharge pipes that bring water out of this pumping plant. We lift it about 250 meters to this point over about, I think it's about a kilometer to get up to there. And then from there, it goes through a 12-kilometer tunnel, flows by gravity down to one of our next pumping plants. But one of the big projects I had just a few years ago over 2 different summers was relining these 2 steel pipelines. They actually start about 100 feet below the bottom of the lake here. And over here, this is just a typical pumping plant. It's one of the larger ones out on the western side of our system, but all of the plants have the canal leading into the forebay, and through however many pumps we happen to have in whichever pumping plant that is, it just lifts it up and then flows by gravity down to the next pumping plant. What this picture is showing, or the graph, is just the lift that we have at each of the pumping plants. So this first plant lifts water about 250 meters, and it flows by gravity to the next plant, it lifts it. But all told, we're lifting water about 915 meters to be able to get it to our last operating reservoir. And then from there, it flows by gravity to the final bit of our system. This background picture is one I grabbed out of our archives. It just shows what the system looks like and how desolate the area is where we have a lot of our facilities. A couple pictures of the check structures. Again, these are what we use to regulate flow in the canal. We also use them to regulate flow or stop flow going into our pipelines and tunnels going across the state. This is a picture I took. We were coming up out of one of the inspections we were doing, and look, it was a nice cloudy, and actually it was raining that day. It was kind of chilly, and I missed it. I was underground most of that day. One of the things as a reliability engineer, we also evaluate these radial gates, and in a 5-year cycle, we're out inspecting every single one of them, making the determination of which ones we need to repair next. Sometimes we'll just pull the whole gate right out of the structure, send it back to headquarters, and refurbish it. And while that's happening, we have dropped in the spare gates that we have. I've also been tasked with redesigning, and have done that, all the cathodic protection system for all these gates. The turnouts, where we deliver water to our customers, can be nothing more than just an opening in the side of the canal with a trash rack. In this particular case, we deliver so much flow and we get so much debris built up. We've got a trash rake that can handle the debris. This particular system I designed a few years ago, this is a very remote facility. We did not want to have people going out to handle the debris. So in this case, we just decided we're pushing the debris back into the canal and letting the downstream pumping plant handle the debris and trash that we scraped off as it was designed to do. A couple other pictures of turnouts. We get a lot of debris built up in the turnouts as the velocities drop, so occasionally we get in and have to clean them out. What happens when the sediment builds up, in some cases it actually blocks the flow meters from giving us good signals, and we're either overcharging or undercharging our customers. In this case, you can also see one of the ribbon anodes, particularly the steel flow meter section, needed to be replaced. This was actually a fun project over here. I was working with our protective coatings crews of looking at better, more efficient ways of maintaining the steel portions of the turnouts. Our safety protocol that we have only allows a person to be in sandblasting or abrasively blasting for 1 hour every shift. And it would take us a week to get through taking care of one of our turnouts. And with the evaluation and the subsequent purchasing we did of one of these blast robots, we were able to cut the blast time down from a week to just under 5 hours, so saving a tremendous amount of time. And that groundwater recharge. Because of the drought on the river right now, our largest recharge facility has been mothballed. Actually, that picture I showed you of the trash rake I designed was for this system. I'm going to take a moment, kind of get up on a soapbox here and talk about this recharge facility. I designed this one back in the mid-90s when I was working for a consultant. I had no idea I'd ever end up working at the Central Arizona project. It's got about a 5-kilometer, 1-meter diameter steel pipe bringing water to the recharge facility. There's a huge pecan grove right here, and then Mexico is just south of us right here. But Tucson Water still uses this recharge facility for recharging their CAP allocations. And the facility has been expanded a couple times, modified. But the point I want to make on this is, as a young engineer who did the design of this, I'm now a senior engineer at the facility maintaining the system. And whenever anything happens on it, because my name is all over the design drawings, I get the phone call. And we're finally getting the SOPs rewritten on this, and I keep getting the workflows to help rewrite the SOPs. So I'm not sure who's all on the presentation here, but if we've got younger engineers, think about the design that you're doing and what the long-term ramifications of the design is based on how it may be maintained. So I'll get off my soapbox now and get back to, okay, this is just a picture of the canal in the southern portion of our system. The previous canal we saw was on the west. This is just north of Tucson, not too far. Here's a turnout facility. We're just turning water out into a canal, and the irrigation district takes responsibility of the flow and the maintenance from here, and then they go on and deliver it to their customers. A couple of other reliability engineers in my group, they maintain and take care of the operations and maintenance road that we have on either side of the canal. We've got protective dikes in certain areas to protect us from overland flows. You can sort of see an old wash here. We've got an undershoot that goes under the canal, taking the drainage from one side of the canal to the other. Having a facility that crosses most of the state, we interrupted the natural drainage pattern. So we hard to see in these pictures, but we've got some overshoot pipes here that do the same thing. And that's another thing that my group maintains. Now we get into the pipelines. This is a picture of one of our large diameter steel pipes. I took this picture as we were coming back out of an inspection a few years ago. We've got the inspection team coming out. Vast majority of our pipelines are pre-stressed concrete pipe, mostly with cylinders. Some are non-cylindered. They go from 6 foot to 144 inch or 12 foot. Typically, we do have some larger diameter steel pipes. And we've also got those large diameter siphons. And a lot of my time is spent working on those siphons, trying to track what's happening with them, in particular the steel and the pre-stress, because we do have a lot of distress of the pre-stressing wires in those pipes. Another great big picture that Jason wanted me to show. This is, actually that first picture I showed of a pipe being repaired is this pipeline. Here it is being installed. Just gives you an idea of the scale of the facilities we have. And this was especially designed and built, what they call pipe mobile, for being able to install the pipes. This is one of our steel pipes. We were in doing an inspection of the coal tar epoxy liner, taking dry film thickness readings. In this case, we're doing an electrochemical impedance spectroscopy test, looking at the efficacy of the liner that appears to be intact. In some places where the liner looks good, it actually is. In other places where it looks good, there are tiny holes allowing moisture to penetrate, get down to the substrate. And that's what we're trying to figure out, is where to go in and do maintenance on these liners. This is the discharge pipe from that first pumping plant I was talking about. Working with one of our inspectors here, where actually I got rope certified to be able to do the inspections on this pipeline because of how steep it is. We're dropping down on ropes into the lower section, doing our inspection of the freshly blasted steel before the contractor puts on the new epoxy liner. This picture just gives an idea of the size of the pipe and what it takes for us to get in and out of the pipe. A lot of ladder crawling. Another picture here of the pre-stressed concrete pipe we were repairing a few years ago. We were either removing the damaged pre-stressing wires, or in some places we left that intact. But then we're doing post-tension tendons to try and contain the hydraulic integrity of the pipeline. We had to completely dig under the pipe, and then rather than try to compact the backfill under the haunches, we used CLSM, controlled low strength material, or slurry or flowable fill, depending on what part of the country you're in. This is a full-size concrete truck coming under the pipe to deliver concrete. We specifically designed the ramps to be able to get these trucks in and out safely. Here we are abrasively blasting with a robot one of the large diameter steel pipes to reline that. And just to show, we do have some smaller diameter things. Here's one of our mechanics working on the sleeve coupling. We had some differential settlement between one of the vaults in the pipe, and had a small leak. Well, so I'm going to get more into now what a reliability engineer does, or at least what we do at CAP to reliably operate our system. Really, reliability is a probability. You can look at it as the probability of success, but we look at it as the probability an item or an asset is going to perform its intended function without failure for a particularly stated period of time in a specifically stated operating condition. I know that there's a lot of specifics to that, but you cannot expect an asset to perform other than how it was intended to, or how it was designed, what was it intended to do. So some of the typical tasks that we do in the engineering department, or the reliability engineering department, we perform inspections, we gather data. In some cases, we have condition-based monitoring systems that gather the data for us and then send it into us via email, via our SCADA system, whatever we may have. But then we analyze the data. From all that data, we develop our preventative maintenance procedures and tasks. We establish the maintenance schedules. We work with our crews. When are we going to go out and do this work? We work around the outages that we can take from operations, or we work within the constraints operations has given us with their outages. We also often determine the repair schedule, and we are usually the ones doing the designing the repairs. So the big thing in reliability engineering is we identify the asset's function. Then we look to see what failures may cause that asset to no longer function the way it's supposed to. We call that a functional failure. Then we look at what the failure modes are that may cause that functional failure. And then we further look at the consequences of those failures, and from that help establish the priorities for doing the maintenance procedures and the priorities of maintenance that we want to do on various assets. One of the tools we use quite a bit is a P to F curve. When I first started reliability, it took me a while to get my head wrapped around this, but it's P to F is the potential for failure, and F is failure. So there's this P to F interval. If we look at condition on the y-axis and time along the x-axis, time can be measured in days, weeks, decades, or it can be measured in cycles or number of operations, depending on what the piece of equipment or the system is that you're analyzing. And our condition is 0 to 1 or 100%, however you would prefer to look at it. I often think of it as a percent or a probability. And when your asset is first installed, it's like new. We can ignore infant mortality and things like that. We'll just assume the facility is operating the way it's supposed to, and it's going to operate in a like new condition for a period of time. And then something changes. On a pre-stressed concrete pipe, a wire breaks. So we've hit that point of P. There's the potential for failure. Failure is now imminent. It's not immediate. It may take several years until more wires break and you hit a limit state. And these limit states for us, serviceability, damage, strength, are based on finite element analyses that have been done for each of the different pipe classes we have. So when you just have a few wire breaks, probably no big deal. The severity of that is low. We just kind of keep an eye on the pipeline. As more wires break, maybe this is what we try to do, is we want to avoid the serviceability limit state, because by definition of the analysis that was done, we've cracked the internal core of the pipe. If we don't do anything to repair it, eventually enough wires will break that the outside of the pipe will be cracked. And if you still don't do anything, eventually that crack is going to join and you'll get leakage. The particular pipelines for which this graph was put together are low pressure pipes, so we're not going to get a catastrophic burst as you do on higher pressure systems. This one's just going to be a leak. What I'm showing here is the data that has been collected on what we call our Jackrabbit pipeline. It goes under the Jackrabbit wash, but it's a very short pre-stressed concrete pipe. It's only got 63 pieces of pipe in it. So what I did on the y-axis is just number the pieces of pipe, and on the x-axis is time, showing every 6 months since 2014 when this condition-based monitoring system went in place. And every time a wire breaks, I get an email. And I've been plotting those emails over the years, plotting those wire breaks over the years, and a trend developed. You can see the downstream section of the pipe seems to have more wire breaks. And then I realized those wire breaks really tend to clump in the warm summer months. So then I took water temperature, and we've got a thermometer in the canal measuring water temperature, and I started plotting the water temperature over here on this y-axis. And I can see when the water gets above a certain point, we increase the rate at which wires break. So still doing analysis, I've taken that information, and all of this, the information right here is from a single pipeline. We've looked at internal inspections where we've gathered broken wire data, the AFO, or our condition-based monitoring system, and I've plotted that by piece number to see just what is going on. Here's just a quick graph of water temperature versus the month and the number of breaks we happen to see in a month. You can see that significant increase during the warm summer months. And I've been looking at the data over time. This is data for the entire pipeline. Whereas over here now, I'm looking at a single piece of pipe in the overall system. I'm trying to predict, based on all the data we've gathered, when we will hit that serviceability limit state that I showed you on the P to F curve, back that out and determine when do we need to go in and do maintenance on the pipeline so we do not hit that serviceability limit state. On our steel pipes, we gather the dry film thickness, or what the thickness is of the liner that's protecting the substrate. This is a plot of the electrochemical impedance spectroscopy. Anything below 10 to the 7th is bad. You're really not protecting that steel anymore. And I didn't realize it until I was going over this presentation. I meant these are from two different pipelines. I meant to have the same pipeline so I could show some of the trends that we saw. But from this plot, we know we need to actually go do some repair on the first few pieces of pipe, more so than the downstream end. Then, of course, we've got to look at our risk, what the risk is. So we use our risk matrices to help with that. And all we're doing is plotting the consequences of what that failure may be versus the likelihood. And from that, you come up with a risk priority number. Some agencies will add the consequence to the likelihood, others will multiply, but it really does not matter as long as you're consistent in how you're analyzing that. And through the maintenance tasks that we're coming up with, we look at whatever may be in a high risk, and we try and pull that down through an increase of sequencing of the schedule or more invasive maintenance that we may want to do, to try and pull us into a very low risk priority number. So for pipelines, I look at an individual pipe piece, then I take that to the overall pipeline to see what the risk may be for that part of our system. This is a picture that was taken of one of our large diameter pipes, and I like it because it shows the teamwork from one of the other reliability engineers. Our reliability engineering supervisor giving me his foot so I can reach higher up, and I'm marking something on the pipe wall from a reading I've taken. One thing I'd like to mention is the reliability engineering versus a design engineer. The design engineer will ask how he or she can make the system work, while the reliability engineer asks how the system may fail to perform its intended function and what we need to do to make sure we can maintain that function. And I'm going to leave everyone with just this thought, but the intent of maintenance is to prevent the failure from occurring. It's not to go in and restore that asset after failure. So as we're working on our engineering projects, we're doing our design, think about the long-term maintenance and think about what the best way would be to maintain our system. And with that, I'm going to say thank you. I appreciate everybody joining me this morning. And if there are any questions, please let us know. Thank you.
Awesome. Thank you, Jim.
Thank you.
That was a great presentation. Yeah, we've got a few questions here. One of the questions, and even when I was living down in Arizona, so I lived fairly close to one of the CUIIC canals, and how much water is lost to evaporation as they're transferring water through these canals? Because I mean, what's the length of the canals, and how much evaporation actually occurs?
I don't know the volume. I've not sat down and recalculated that, but it's about 1.5% of what we move through the canal is lost to evaporation. It's not that much considering how much water we're moving. No,
very true. I got a few tough ones for you now.
Okay.
So you kind of talked about a little bit about what I consider smart infrastructure. You're monitoring the wire breaks. you're getting emails back that, that kind of give you the event status kind of thing. Are there any other assets in the CAP system that are monitored in the same way? Like there is like smart infrastructure and sensors, is that beyond just the pipes, like the Trenchless pipes? Is there other assets that are monitored similarly?
We do not monitor any of the other pipelines that way, but within the pumping plants, we've got an entire condition-based monitoring system or project that we've been working on. We remotely monitor the temperature of the pumps, the vibration of the pumps, the oil in the transformers. Those are the three that come to mind specifically. But then with the flow meters we have, we can monitor the flow going through each of the pumping plants and each of the turnouts, and then we can determine if there's an unbalance in the system where we may have a problem.
Okay, no, that's good. Thank you.
Okay.
Another question here for you.
Yes.
This is big picture. I'm not sure if you can respond or provide any input on this, but can you discuss some of the challenges and risks that you kind of see for CAP moving forward over the next decade or two? These challenges and risks related to things that might change or infrastructure. You can kind of choose where you want to take the discussion there. What do you see as big challenges in the next 10, 20 years, and what's CAP doing to kind of mitigate these things and adjust how they do business?
Boy, I'm not sure where to start with that one. That's a good question. One of the things, we are in a drought condition right now, but over the years and past, we established the groundwater recharge facilities. We have been recharging over the years. We're now looking at putting in well fields and extracting water out of the recharge facilities. We're working with our customers to be able to wheel water for them. Like the city of Scottsdale has a recharge facility that they purchased from a different entity way out in western Arizona. They would like us to move water for them. So we're working on wheeling agreements and water quality aspects for turning water into the canal. There's another entity, the Salt River Project, SRP, who delivers water to portions of the city. We are working with them for an interconnect facility. Right now, we can deliver water to them if they need it, but they would like to be able to give water to us so we can move water for them. We're also seeing tremendous growth in the Phoenix, or in Arizona in general, but in particular Maricopa County where Phoenix is. So we're seeing a lot of encroachment on our facility. Because of how deep and fast we move the water, our entire facility is all fenced off, but we get people cutting the fence to go fishing, go swimming. Some of the areas that we have, the canal itself is fenced off, but not all of our property. And we're seeing people kind of encroach on the easements we have and build things. In some respect, though, having that growth come in is helpful. The project I had a number of years ago was trying to provide potable water to some of our remote pumping plants. And we did that with internal treatment systems, but now we're seeing the growth coming closer to us so we can tap into the municipal system and not have to treat our own water. I can continue with more, but that's kind of a part of just some of what we're trying to do.
So there's a question here, and I was kind of curious myself. You showed some pictures here of the pipe and that large pre-stressed pipe, the largest pipe in the system there in North America, I think you remember, or was it the world? The question is, it looks like there's wires or rods that are wrapped around the outside of the pipe.
Jason, I lost you there. I heard you say the question is.
Okay, can you hear me now, Jim? Jim, are you there? Jim, can you hear me now?
Yes, not sure what to do. Is anybody there?
Megan, by chance, is it me or Jim?
It is Jim that has lost internet, I believe.
He's moving on my screen, man.
He is moving on my screen as well. I'm wondering if his headphones dropped out. I'm going to send him a note in the chat here really quickly.
Yeah, so just hang on the line here a little bit. We'll get Jim back. There's a few good questions here. So I see questions here from Mike, Dylan, and Joe. Oh, there's a whole bunch of them. And here, expensive one. And David. Interesting. Jim is on the. Jim, are you able to hear us? Uh-oh.
I unpinned him from the screen until we get him back.
Okay. Well, we'll see if we can get Jim back here. But in the meantime, don't give it a little bit of patience here. What I want to do here is just we'll do maybe a little bit of a wrap up here. Oh, Jim, you back? Okay. The Jim, yeah, that's a good point here. So what we can do here, there is some good questions here, and what we'll do is we will address these questions offline. I'll give them to Jim, and Jim will respond. I appreciate everyone's patience here, and apologies for the connection issues here. But yeah, just really want to thank Jim for doing this. Jim, I've known Jim for a long time. We were working together on some of the American civil engineers pipelines that we didn't work, and he'll soon be my academic brother, so to speak. As he'll have his PhD here, hopefully, he's pending here in the early 2020. So it's today to speak with us. So yeah, thank you very much, Jim. Sorry you can't hear it. Appreciate everybody being here today and attending, and just want to thank all of the CUIIC members that are for all the members or people, the companies that are members of CUIIC. You can see them here. If you are interested in joining CUIIC, definitely reach out to CUIIC.ca, and we've been in operation about a year and a half, and we'll continue delivering excellent content presentations like this. So that's it. I don't think we can get Jim back. Oh, Jim, you're back.
Sorry, I had to go out and come back in. I apologize. I don't know what happened.
No, that's okay. Appreciate you coming back. No, there's still a good number of people on the line.
Good.
And,
You'd started asking me a question about pre-stressing wires, and that's when I lost you.
Yeah, no, that's good. Okay, so we'll ask some questions here now.
All right, sorry about that.
There's way too many questions now. You're in trouble.
Uh-oh.
So there was earlier in your slide, there was in your presentation, I'm just going to go back to it for you. Here we go. There's pictures of this large pre-stressed pipe, and we held these wires on the outside. And the question is, why are the pre-stressed generally inside? Why are these wires on the outside?
Oh, okay. That was the repair we were doing. We wrapped the outside of the pipe with external post-tension tendons. So that's just a method of repairing pre-stressed concrete pipe.
And so those tendons are in direct contact with the outside of the pipe itself, kind of thing?
The tendons are encased in a I can't remember if it's polyurethane or polyethylene plastic coating, and they're injected with grease, and then they're tensioned around the outside of the pipe, and then we actually shotcreted them for additional protection. But it's called external post-tension tendon repair.
Okay.
Other entities will use carbon fiber, but because of the cost, we went with the post-tension tendon, and we have done that in the past, so we're familiar with it.
Excellent. I have another question here. What's the difference between design and reliability lifetime? Can we improve the design life with a good reliability program? What is your thoughts? What is the difference between design and reliability lifetime?
When things are designed, they're designed for a specific period of time. God, I hate to say it that way. There is a design service for which things are designed or considered, and that has more of an economic standpoint. I've been using the term when things are designed. I'm hearing an echo on myself. I talk about our pipelines as being forever assets. They were designed with maybe 100-year design life, but now we're trying to look at the functional failures and do maintenance and or repair to extend the lifetime. Matter of fact, we just are in the process of wrapping up a life cycle cost analysis on our 2 large diameter steel pipes, realizing that using epoxy to protect the inside of the pipe is just not sustainable. So now we're looking at a cementitious liner where we know you've got about 100-year life service of the concrete or cementitious material. So we're trying to apply that instead and get away from every 30 years repairing the epoxy liner. So, same with our pumps. They may have only had a 40 or 50-year design life, but we're hitting that point, and we don't plan to replace these pumps. These are 65,000 horsepower pumps encased in concrete, so we're doing lots of maintenance and reliability studies on them to see how can we extend their useful life. So we're not looking at short periods of time. We're looking at things in terms of decades, if not centuries even now.
Very good. A couple quick questions here. What's the water source for the recharge facility?
The water we pull off the Colorado River is the water that we put in the recharge facilities, or the water that we deliver to Tucson Water is Colorado River water, and they recharge it in their facilities.
Okay. Got some more canal questions here.
Okay.
How wide is the right-of-way around the open canal? And are there any bridges allowing to cross over the canals?
The right-of-way width changes. I know the rights-of-way for the pipelines. I don't remember for the canal. We have security fences along the canal. On the right side of the canal, and right side is always as you're looking downstream, there's a 10-foot easement or right-of-way that we still have, but we maintain that as a trail for Arizona. So the right-of-way varies depending where we are, but there are many, many bridges that cross us, especially when we get into an urban area like Phoenix or Scottsdale. Typically every mile there's a bridge that crosses us. And we also have out in the more remote areas wildlife bridges just for wildlife to be able to move across the canal.
Yeah, I mean, it's interesting when you live in Arizona, these canals are everywhere. I mean, they're going right through Phoenix, they're going through Scottsdale. It's just integrated within. It's just like another road, essentially going through town. And there's regular bridges, the streets go over top of them, and then it's pretty natural looking actually. Just like they belong there. So yeah. Got another one here for you. This might be a little bit open-ended. Let's see where it goes. You've spoken about maintenance on your pipeline. Can you tell us about your program for pump stations and electricity supply?
A little bit. I'm not that familiar with the maintenance systems for the pumping plants. For electricity, that one's a little easier to answer. We used to get all our power from the Navajo Power Generating Facility, a coal-powered or fueled power plant in the northeastern section of Arizona. That was decommissioned a few years ago. So we now purchase power on the open market. We've got a whole group in our admin department that takes care of the purchasing the power. Sometimes we'll get power at an extremely cheap rate, and we'll decide to shut the pumps down if we can and sell that power to make money and run the pumps later. So it's not something that I get into. I'm just aware of it because it sometimes affects the outages that I'm trying to take, or it affects our outage extension that we can have. But we do have regularly scheduled maintenance for all the facilities, our pumping plants, the discharge valves, the electrical system in the plants, the discharge valve operating systems, the potable water systems we have. We have equipment maintenance plans for all of our assets now, and the last ones to get developed are ones I just completed last year on all the pipelines.
Very good, thank you.
Thank you.
Okay, here's a good one. We'll see where this one goes. In your view, how alarming is the fact that groundwater replenishment was paused this year due to drought conditions and decreased allocation from the Colorado River? How do you see this playing out over the next 10 years? And just like looking at the challenges that are facing the Colorado River and the main downstream users.
Not sure where. That's a good. Oh, I don't.
Is that beyond the scope of reliability engineer?
Part of it could be, yes, but that's a very good question, and that does kind of bother me that we have had to stop our recharging right now. But when the recharge facilities were designed and built, we knew that we're pretty certain that that would be the case at some point in the future. We ceased to pump ground or ceased to recharge. Now we're trying to extract that water out to augment what we're not able to pull off the river. Hopefully, the river will start flowing more water again is the long-term hope. None of us can really tell the future. So we are looking at other sources of water. There's talk of desalination, either down in Mexico or over in California, and moving the water to us. Potential of trading water with other entities. That's one reason SRP is looking at being able to give us water. They get water off the Salt River and the Verde River here in Arizona. And if we can move water for them, that would then help us. The city of Phoenix just put in a very large pipeline taking water from the southern part of the city up to the northern part of the city, where I live in the north part of Phoenix and we rely on CAP water, whereas the southern part of the city gets more SRP water. So there's a lot of inner workings amongst the municipalities as well, trying to look at how to augment water. And then we are certainly trying to conserve water as well.
No, and I don't think that's just a problem that you see down in Arizona. I mean, even here, I mean, I know that just even around Edmonton where I am, I mean, the last 3 years we've been, short water. That just hasn't been raining. So I mean, it's an issue everywhere. It's not very good. This is a good one, and I've always been kind of curious about this as well. Is there a bypass system? Should there need to be, like, if there's a emergency kind of repair to a canal or a big pipe, or some kind of contamination event, is there such a thing as a bypass, the ability to bypass anything there on these canals and pipes?
Yeah. The way the system is designed now, no. So if the Salt River siphon or Salt River pipeline, which is a big pipe, we shut down for 6 weeks to work on it, we had to let our customers know years in advance so they could build reservoirs or get wells rehabilitated to have water for that period of time. One of the things we're looking at is bringing a couple of abandoned pipelines back into service so we can do work on a couple of our large pipes. If need be, we can do low capacity pump arounds. We lost a section, almost an entire mile of pipeline a few years ago to a big storm. And we were still able to move water, but we were moving it with a lot of dirt as well. So we had tremendous turbidity issues downstream. We ended up shutting the canal down for a few weeks, pulling all the debris out, running water against the dirt for the next year till we could take another outage and repair the liner. A little bit further downstream, we were doing similar work, and we put in a couple of inflatable cofferdams, and with half a dozen pumps, pumped a small volume of water around. So that there are things we could do in an extreme emergency. Fortunately, we've not come up with anything nothing that drastic has happened to us. They've been small, minor things that we can handle a short duration outage.
Questions keep coming in, Jim. the people keep staying, so you're going longer here.
No, it's great. It means that
it's good. I
appreciate that.
So this, how is the question here is about pollution. So how is pollution taken into consideration in reliability assessments? And it's kind of interesting. I'm just going to mention here about turbidity and ground, and I'm not sure. Is there any kind of I guess I'm not sure what the context of pollution is in that question. But do you have any thoughts there?
When a little bit with the turbidity, when we were recharging, we would keep an eye. We've got a turbidity meter. Actually, we've got water quality stations throughout the canal. Every I don't know, I'm not sure quite how sporadic they are, but turbidity is one thing we measure. And when we see a spike in turbidity, or we know that one of the rivers releasing water into Lake Havasu, or one of the dams that's going to release water to a river that provides water into Lake Havasu is usually very turbid, we monitor that and we'll shut off our groundwater recharge facilities. When we're pulling water out of Lake Pleasant, if we see a change in water quality quite a bit, we'll let the cities know so they can change their treatment system. But in terms of a contamination in the water, we don't do anything for that. Hopefully we have enough volume coming through there that it's going to dilute anything. We've never had a problem with that sort of contamination. There are utilities that cross us, and the city of Phoenix or Scottsdale had a sewer line that broke once coming across us. So then we still continue to move water, hopefully we're diluting that. Then we let the downstream customers know, hey, this is what happens, so expect this at your treatment plant. And then at each of our pumping plants, in the forebay, there are big trash racks that the water has to go through. And I think they're 4-inch spacing on that. So it keeps most of the debris out of the pumps. And each of those pumping plants have trash rakes that we can remove the debris. Usually it's weeds, a lot of tumbleweeds, but it could be cattle or wildlife that end up in there. So from a reliability standpoint, I guess that would be how reliable are the trash removal systems that we have.
Yeah, no, that's good. One of the things I noted when I lived down there, and I remember going around between Phoenix and Tucson, there's so much groundwater being kind of extracted, and there's subsidence, that occurs, right?
Yes.
How does subsidence kind of impact the canals and pipelines that you're looking after? Is there an issue there?
There is. One of the very first projects I had when I started at CAP as a project manager was managing a project to raise the lining through North Scottsdale. There had been so much pumping over the years that the canal had actually sunk. And we were starting to move water against the way the canal is designed. There's a concrete liner that comes up, and then there's earthen freeboard that comes up a couple of more feet. And we never want to do what we say run in the dirt. But we had so much subsidence in that area that we were actually running in the dirt for a short section of short section of the canal. So we went out there and raised the O&M road a little bit, raised that earthen 2-to-1 slope, and then increased the height of the 1.5-to-1 side slopes of the concrete for, I don't remember how many miles we did that. In other parts of the canal, when Reclamation did the design, they tried to account for subsidence, and the liner is actually higher than it needs to be right now, and we've not seen subsidence there.
Subsidence, so that's like, we're not talking about, it's a bigger, like what I'm trying to say, it's a wider area thing. There's not a specific location where the subsidence would all occur. at a point load kind of thing. Is subsidence that generally a longer distance spread out kind of issue?
Yes, more of an area wide. Excuse me. We were able to determine where it was along our canal because we go out and routinely survey and regrade the O&M road. I don't know what the impacts were to the surrounding properties around us.
Mhm.
I just focused on the canal itself, and fortunately, it did not happen where any of the check structures were. It was just in between, and the check structures probably have a bigger foundation, is why they did not see any subsidence.
Excellent. Thank you. Here we go. Let's see how you handle this one. So, recent semiconductor between construction and CUIIC's impact available water. And I guess it's the question here. The next part is kind of about, this is probably where you need to focus on is, like, are the pipeline size to meet future demands with these kind of plants and growth in mind? So I think that's where the question is more focused, right, in terms of growth and capacity.
Right, and one of those new semiconductor facilities is being built about 4 miles north of me, so I see it quite a bit. Those facilities get water from the cities or the municipalities in which they're built. So there's the Taiwanese semiconductor facility just north of us gets water from the city of Phoenix. The allocation of water that Phoenix gets from us will not change just because a new facility has been built. The same with, I think, the Chandler area where Intel has a couple new facilities going in or being expanded. They get their water from Chandler. We're not going to increase the allocation of water, and we're limited to how much water we can pull off the river. However, where that gets into, and this is a study we have been looking at for a while, if we want to move more water, say, I mentioned earlier, Scottsdale had that recharge facility where they'd like us to wheel water for them. We are looking at increasing the capacity of our system, either by raising the liner, but potentially putting in additional pipes. Like I have looked at a couple of our large pipelines out west, maybe putting in a small 10 or 12 foot diameter pipeline to help bring more water around for wheeling. And we've even looked at, can we increase the capacity of our pumps, or do we need to add pumping capacity somehow if we do start wheeling additional sources of water? So the water that we get, it comes off the Colorado River, and we're limited to what the Department of the Interior will allow us to pull off. But we can and are in the process of getting these wheeling rights started with other entities to move water for them. So long story is, yes, we're looking at ways of increasing the capacity.
Very good. What are some of the most challenging environmental impacts from the canal or tunnels that need to be overcome?
Boy, that was trying to think where to start. There was significant environmental mitigation that had to occur for the Central Arizona project to be built. I don't know all the details with that. I do know that the reclamation has put in several fish barriers for Arizona game and fish, that the Central Arizona project is slowly taking over the maintenance of that. Our canal typically runs from the west towards the east and then cuts to the south. So we get a lot of, and the typical drainage of the state is from the north to the south and from the east to the west. So along what we call a green up area on the upstream side of the canal, we maintain that for natural habitat. We do not go in and clear debris. We just kind of let that grow wild for the wildlife. And of course, in the urban areas, that's not the case. But in the more remote areas, as an example, at Mark Wilmer, the sump from that plant discharges back into the forebay, which is still considered a water of the U.S. So we're very limited to what can go into that sump. So some of the projects we do, we've got to come up with other drainage issues or other drainage designs on some of the projects we're doing in the plant. So I don't get into the environmental stuff that much. And since we're an already built facility, a lot of the mitigation has already taken place.
No, it's good. No, it's true. Because how long have the canals been there?
The construction started in 1973. We started moving water for the first time in it was either 85 or 86. And we finished construction of the Waddell Dam and pump plant in 93 or 94. So it took a long time to get the whole thing built.
Yeah. No, very good. 2 more questions, then we'll wrap it up here. Is there a significant sediment deposition in the canal, and how is that dealt with?
Can we skip that question?
What question, Jim? I don't remember the question.
Oh, the Reliability Engineering Group just finalized a report on sediment depositions and how sediment affects us. And there is a tremendous amount of sediment. It doesn't not build up in the canal itself because we're moving at about 3.5 feet per second. Where the sediment comes into an issue is at some of our turnouts, they have their own forebays and the water will get into there. And we have actually had so much sediment build up that we're not able to get water to the customers. So we've had to go out with long reach excavators and get out as much as we can. The sediment also builds up in the forebays, and every year our biologist goes out and maps the sediment mounds. And I wish I could find it quickly. I have a picture of a cow standing on a sandbar in the canal. We had so much sediment built up. So when we have the opportunity, we go out and try to remove it. When we were doing some repair work on the Salt River pipeline, we took the canal. Well, I say we took the canal down. We completely dewatered that next mile of canal, and for several weeks had backhoes in the canal or in the forebay with the cranes scooping out all the debris. So it is an issue. We haven't come up with a reliable method of dealing with it. We're still trying to decide how much of an issue it really is, and we're looking at the cooling water systems, the strainers, the filters in the pumping plant to see how much the sediment may be affecting us there. So it's something we're constantly dealing with, and we do not have a good answer.
No, that's good.
Thank you.
All right. I'm going to give you your final question here, and then we'll wrap it up. And this is kind of going back maybe to your presentation in general. Can you give some background or commentary kind of about how reliability engineering as a discipline or a practice at CAP kind of started? Was it like an evolution, or was there a certain need that just kind of happened? That there was an instance that the light clicked on, kind of thing. You know what I'm saying?
I understand the question. My first response is I don't know. And the reason I answer it that way, I was upstairs in the engineering department for many years, probably I think 10 or 11 years before I came down to the reliability engineering department. We've always had a maintenance engineering group, but I think as the maintenance group started looking at things more long-term, realized that reliability is something we need to be considering. So they started, and I say the maintenance group started a reliability engineering department, and I was moved down to that department about 2 years after it started. And what the reliability engineers do is look at the system long-term. We've got 3 civil engineers who are reliability engineers, 2 electricals, 2 mechanicals, and we're still trying to hire another electrical engineer. So we're very discipline specific, and the reliability engineers look at the long-term functions and long-term reliability of the overall systems, where the maintenance engineers are more hands-on with our technicians and our field crews trying to fix things quickly. We're studying and analyzing things more. I saw there's some formatting things popped up on the presentation I gave, but every slide I had for reliability engineering says, reliability engineer, analyze data. We are constantly analyzing data, looking to see how can we best help to maintain the system. And it goes all the way back to design. I've given several talks on reliability-centered maintenance analysis. And now our engineers upstairs who look more at capital projects are starting to look at the reliability-centered design analysis and build reliability into everything we do.
Yeah, very good.
Thank you.
Okay, Jim, I'm gonna release you and let you go. Definitely appreciate you taking the time today to join us and give the presentation for CUIIC. I've noticed the numbers are increasing as the questions go on, so I'm not sure what's, it's kind of interesting that more people are joining now that you're answering questions. So that's good.
Well, thank you, Jason. I appreciate you asking me to give this presentation. I've enjoyed putting it together. I enjoyed giving it. I understand the presentation will be given to people, and my contact information is on the last slide or second to the last slide. So if people have questions, reach out to me, please. I enjoyed talking about this. You're welcome. Thank you.
Thanks, Jim. All right, everyone, have a great day, and we'll see you at the next webinar there in October. Coming up here in October. See you, everyone.
Thank you. Bye.